Okay, let's look at this one. So it says engineers determine a monument currently 18.2 feet tall will sink 4.1% every decade. Okay, so initial value is, okay, that's easy, hopefully. Okay, so the 1 decade, is it growth or decay? Shrinking. So what is the 1 decade decay factor? It will sink 4.1% every decade. Okay, so it's not going to be 0.041 because the decay factor represents what about our amount? What you keep, what remains. So the percent change here is negative 4.1%. Oh, so let's do that first. So then the 1 decade percent change is what they're giving you. That's the negative 4.1. So then, but the multiplier then is what you keep, the portion that you keep. So it's going to be 100 minus that. And 100 minus 4.1 is what, 95.9? So then it'll be 0.959. Right? 100 minus 4.1 is 95.9%. So that's the amount of height that's retained or kept every decade. So you're going to multiply every decade, you're going to multiply by 0.959. Okay, so the function h that determines the height of the monument in feet given d number of decades. So it's going to be h of t, d, equals initial amount, 18.2 times 0.959 to the d power. Because every decade you're going to multiply by 0.959. So after d decades, you're going to multiply by 0.959 d times, right? This says keep repeat. This is how many times you multiply by 0.959 d times. So after 3 decades, you will have multiplied by 0.959 3 times. Okay, so it should make sense. Remember, when you see exponential form, you're going to think repeated multiplication. You see that, you think, oh, I'm going to multiply by 0.959 times 0.959 times 0.959 for however many decades go by, because it's once per decade. Okay, represent the height of the monument, 17 years. So what, in this definition here, what's function notation? What is function notation? Which represents, in general, represents function notation? Output, okay? So it's going to be the h of d. So when it says use function notation, we're going to do it right here. 17 years is, but the input is decades. 1.7 decades. 17 years is going to be 1.7, and then the value, we can just let WebWork do the math for us, okay? Let WebWork do the math for us. So we can, that's what it'll be, 18.2 times 0.959 to the 1.7. Okay? Suppose the height of the monument is measured once a year. Use your function above graphing calculator to determine how many years it will have a height less than or equal to 15 for the first time. Enter as a whole number of years. Okay, so we need to do a graph solution of this. So let's do that. So we're going to graph our function 18.2 times 0.959 to the x, and then we know that x is decades. And so here's what the graph looks like, and we just want it for x greater than 0. Okay, so here's our graph of this. And we want to know when it's less than or equal to 15 for the first time. So you can, is the height of the monument, is that our x coordinate or our y coordinate? Y, right? So the independent variable is decades. That's the x-axis. And the dependent variable, our output, is the height. So I can say y equals 15. And let's zoom in on what's going on there. So I have this point here, 4.619, comma 15. Okay, what's the meaning of that ordered pair? 4.619, comma 15. What's the meaning of that ordered pair?
4.619 decades, the statue will shrunk to 15.
Nice. She said after 4.619 decades is when it will have shrunk down to a height of 15 feet. Okay, and so then but it asks for years. Okay, so how many years is that? 46.19 years. So we got to think about this here. So after 46 years, has it reached 15? Has it shrunk down to 15 feet yet? At 46 years? No. It's in the 47th year, right? So after 46 years, it's still going to be a little bit taller than 15. And in the 47th year is when it will, a little bit into the 47th year, it will reach down to this height of 15. Determine how many years the monument will have a height less than or equal to 15 for the first time. So after 46 years, it's still taller than 15. So it's at 47 that it will be below 15 for the first time. Questions on this? Anybody have a question on this example? Okay, cool. So we did the car depreciation at the end of class last time, right? Was that the last thing we did? Car depreciation? So let's pick up there. And we talked about, we were talking about multi-unit . So let's go back to this and let's look at, so what would the per century decay factor be? So if our 1 decade decay factor is 0.959, what would the 1 century decay factor be? Or in other words, what do you end up multiplying by every century to get the new height of the monument? So if you're multiplying by 0.959 every decade, then what do you end up multiplying by every century to get the new height of the monument? 9.59? So after 1 decade, so in 1 decade, what do you multiply by in 1 decade? What about in 2 decades? Over 2 decades, how much would you multiply by? So the 2 decade decay factor would be 0.959 times 0.959, because 2 decades go by. Every time a decade goes by, you multiply by 0.959. That's the decay factor. So therefore, every year that goes by, we keep multiplying by 0.959. So in 1 century, how many times will we have multiplied by 0.959? 10. So the 1 century decay factor is 0.959 to the 10th. And what did you get for that?
0.6579.
0.658. So our 1 decade decay factor is 0.959. Our 1 century decay factor is 0.658, or 0.959 multiplied 10 times, because every year you multiply the output by 0.959 to get the next year's output. So over 10 years, you will have multiplied by 0.959 10 times. What's the percent change every century? So the 1 century percent change. I'm going to call on someone. Everyone do it. I'm just going to call on someone at random. So what's the 1 century percent change? Okay, yes. How'd you get it? So you 1 minus this. So he wants 1 minus this number here, which is 0.4. Nice and loud. 0.342?
Yes.
So therefore the 1 century percent change is?
4.2%.
Agree with that? Percent change. Negative. If you said percent decrease, it would be positive. But if you say percent change, you've got to have the negative on there. That's important. If you say percent decrease, now you're assuming it's a decrease, you can report it as a positive value. But the percent change, how much it changes, negative 34.2%. Every century. Okay, so this is the idea of, in a given situation, there's lots of decay factors or growth factors, whatever you have. And that's what we talked about at the end of class last time, and you had that last web work problem about multi-unit decay and growth factors. So let's continue on that conversation. Questions on that? Right there. Okay, so where are we at here? Let's do this one. So initial mass of 50 micrograms in a Petri dish doubles every 7 minutes. Complete the following table and find the 7-minute percent change. So complete the table if it's doubling every 7 minutes. And find the 7-minute percent change. That shouldn't take long. Try that. Okay, 100. And then after 14 minutes, 200 and 21 minutes. Doubling every 7 minutes, piece of cake. Okay, so now what about the 7-minute? So I should say, what is the 7-minute growth factor? What's the 7-minute growth factor? 2, right? Therefore, what's the 7-minute percent change? 200%, right? Okay, this is where it gets dicey. Make sure you have this. Growth factor is part of that growth factor. 1 of that growth factor has to be what you had before. And then the rest is how much you increase by. So it's not 200% increase. So you got, remember, it's 1 plus the percent change. Okay? This one is, you're going to keep what you had before. So in that multiplying by 2, one of that is what you had originally, and then the plus r is how much you increase by. So in this case, 7% change is 100%, right? 1 plus 1 makes 2. 1 from what you had before plus 1 additional. So that's the percent change, 100%. Okay, so now we're going to take a look at what we call partial unit growth factors. So we looked at multi-unit growth factors. So what we really want to know is what's the percent change and what's the growth factor every 1 minute. Okay, so here's how we're going to do that. So we don't know what the 1 minute growth factor is, so we're going to call it B. Okay, so B let B be the 1 minute growth factor. Okay, so let's see if we know what's going on here. If B is the 1 minute growth factor and we start with 50 micrograms, then how many micrograms do we have after 1 minute? If B is the 1 minute growth factor and we start with 50, how could you express the mass after 1 minute? How about in the back? How would you express the mass after 1 minute if you start with 50 and your growth factor is B? How about here? And what's your name in the gray shirt? Elijah? What do you think? Not too sure. Next to him. What's your name? Chris. So we're starting with 50 and our growth factor is B. How much will we have a minute later? Yeah. No, we don't know what B is. What is it? 50 times B. What is a growth factor? It's a multiplier on output to get the next output. It's a multiplier on the output to get the next output. So we got an output of 50 and we want the next output. So what do we do to get it? Multiply by B. That's what the growth factor is. So it's 50B. Okay, now what is going to be the mass after 2 minutes? 50B squared, right? So every minute you multiply by the growth factor to get the amount the next minute. So it's going to be 50B squared. Or 50 times B times B. What about after 6 minutes? You're going to have multiplied by B how many times? 6 times. So it'd be 50B to the 6th. This is the essence of what we've been talking about the last week with this exponential growth. Repeated multiplication on the output by the growth factor to get the next output. What about for 7? What would it be for? So we got 50B to the 6th is how much we have after 6 minutes. So what about after 7 minutes? 50B to the 7th. But we know what that is. We know what our mass is. So 50B to the 7th is equal to what? 100. Okay? 50B to the 7th we know should be 100 micrograms. Therefore, this is how we can figure out what B is. So we got 50B to the 7th equals 100. Therefore, B to the 7th equals 2, 100 over 50. And how do we solve for B? Yeah, you're going to take the 7th root of both sides to the 1/7, right? Both sides to the 1/7 or the 7th root. So this is what the value of b is. And someone got a value for it? 1.104. Okay, so we got the 7-minute percent change. Therefore, what's the 1-minute percent change? (10.41%). Because we know that 1-minute growth factor is the 1.104. The 1 means keeping what you had before plus the increase, 10.41% increase every minute. Okay, so now I want you to find the 4-minute growth factor and percent change. What's the 4-minute growth factor? And express it, so express it exactly, okay? Express that 4-minute growth factor as an exact amount, exact value, and then find the percent change. Okay, we'll pick that up later. So, Jose, you're up. How'd it go? What was the 4-minute, how'd you get the 4-minute growth factor? Oh, you can't talk. Okay. Who's your partner in crime here? What's your name?
Matt.
Matt.
So I plugged in 4 times so basically I did 50 times 1.1042 4 times.
Okay.
Which gave me 74.275. And then I subtracted that from 50.
Okay.
Which got me a increase of 38.14%.
Okay. So you did the percent change first. How can we get the, so, okay, that's okay. So how can we get the 4-minute growth factor kind of pretty, like, easily here, and kind of in one step? So how can we get the 4, we have the 1-minute growth factor now, right?
Okay.
Which is this 2 to the 1/7 or 1.104. How can we get the 4-minute growth factor out of that? Matt, how can I get the 4-minute growth factor from the 1-minute growth factor? Yeah, because so what does the 1-minute growth factor mean? It means every minute we multiply by, and this it's going to be 2 to the 1/7, right?
Yeah.
So every minute we multiply by 2 to the 1/7. So then what happens every 4 minutes?
You multiplied it 4 times.
That's right. And how do we express that? We multiply by 2 to the 1/7 4 times. So how do we express that?
Like 4 times.
Not 4 times. It's going to be 2 to the 1/7 times 2 to the 1/7 times 2 to the 1/7.
So 2 to the 1/7, and then the exponent is 4.
There you go. So there's our 4-minute growth factor. 2 to the 1/7, 2 to the 4th. And this would be an exact representation. If you use that decimal, if you use 1.104, you're just getting an approximation. Okay? So this 2 to the 1/7 to the 1/4 then represents that exactly. But then to get the percent change, we need to get what that is. And so he got, what, 30? You said 38?
Yeah.
Did someone else get that? Is that what this equals?
It's not that loud.
All right, so this is also, you could also express it as, is that right? So that's an approximation for this, 2 to the 1/7 to the 4th. That's our 4-minute growth factor. Therefore, percent change is? Yeah, pretty dang close to 48.6% increase every 4 minutes. Okay, so what would be the mass after 18 minutes? So let's see if we've picked up anything here. What's the very simplest way to get a value for the mass at 18 minutes? Given the information that you have up there. Would that be the mass? So you took 2 to the 1/7 to the 18th. What would that be? What would that number represent right there? That's important, but what would it be? 2 to the 1/7 to the 18th would be, what would that represent? That's a growth factor. That would be the 18-minute growth factor. So if you wanted the mass, how could you get that? That's not a mass, right? That's a multiplier. How could we get the mass at 18 minutes using that? What's that? Yeah, so if we times it by 50, right? If we times it by 50. Okay, so that's valid. That will get you the mass at 18 minutes, but it's actually, and there's an extra step in there because we had to find the 18-minute growth factor and multiply by 50. So anyone got it more streamlined? Yes, sir.
You take the 4-minute growth factor
Right.
and multiply by 20
Right. So we could start, instead of starting at 50 and multiplying by the 18-minute growth factor, you could start at what? 200, which is how much you have at 14 minutes, and multiply by what? Multiply by the, so we're at 14 minutes. What growth factor would you need to multiply by to get the mass at 18 minutes? The 4-minute growth factor. So it would be 200 times the 1.486. That would be the simplest way. You've got the 4-minute growth factor. You've got how much you have at 14 minutes. Boom, multiply them, and you have what you have at 18 minutes. But both are valid, so this is also valid. It's just you got kind of like one extra step there. Doesn't that make sense? So you got to be thinking in terms of growth factors. It's a multiplier on output to get the output, what? C units later, right? Okay, so how about use the 4-minute growth factor to find the mass at 15 minutes. Can you use the 4-minute growth factor to find the mass at 15 minutes using what else you've got up there? Can you figure that out? Use this 1.486 to get the mass at 15 minutes. It's a little puzzle. Okay, so how can we use the 4-minute growth factor to get the mass at 15 minutes? Anyone figure it out? Yeah. Yeah, go ahead.
Okay. Since we already know the 7-minute factor, I took the 4-minute growth factor and times it or squared it, then multiplied it by the 7-minute mark.
7-minute
Mass.
mass. Yeah, right. So if you're at the 7-minute mass and you went 2 4-hour periods, that would take you to 15 minutes. So how do we advance 2 4-hour periods? 1.486 squared. So mass at 7 minutes, and then you multiply by 2 4-minute growth factors, you're going to get the mass 8 minutes later. So that would be the mass at 15 minutes. And what was this again? This is the mass at 18 minutes. Oh, we have that up there. Okay, so let's practice. So this is the idea of partial unit growth factors. Given a growth factor, then we're looking at a unit of input that's a fraction of what we had before, right? So we knew what the 7-minute growth factor was, and we figured out what the 1-minute growth factor was. That's the idea of a partial unit growth factor. Okay, so read that blue thing up in the upper left corner, if you can read that. So it says the body removes 85% of ibuprofen present every 5 hours. So every 5 hours after you take ibuprofen, your body removes, or 85% disintegrates or is flushed out of the body. Okay, so let n be the number of 5-hour periods since taking the medicine. What would a function? I think you guys should just work on this. Okay, no, we'll do the beginning together. All right, so n is the number of 5-hour periods, so we need a function f of n that gives the amount of dose remaining in milligrams given this setup. So n is the number of 5-hour periods, and the body removes 85% every 5 hours. So function f of n. Let's see, what do we got here? Where's Chris Wilson? Chris, oh, I already called you on. So you're off the hook. Where's Ian? All right, Ian. Tell me about this. Do you come up with this function here? F sub n? F of n? 500. 500. He wants 500. And why is it 0.15 and not 0.85? Okay. Why'd you do that? I mean, why shouldn't it be 0.85 there? Right. So remember, the decay factor is what's kept, what remains, what you hold on to, not the amount that you decrease. So this is the amount of decrease, 85%. So the decay factor, you're going to multiply by 0.15 to keep 15% every 5 hours. Okay, do we like it? All right, so what does that mean? So if we had 500 here, how could we easily find the dose after 5 hours? So we've got 500. What would we do to find the dose after 5 hours, 5 hours later? Divide by something or multiply by something? Multiply by 0.15, because that's the 5-hour decay factor. I'm going to multiply by 0.15, and what does that give me? 75. Okay, so now let's do this derivation process again. We're going to let B equal the 1-hour decay factor. Okay, so if B is the 1-hour decay factor, what dose do I have remaining after 1 hour? Let's see. How about in the tie there? What's your name? Logan. If B is the 1-hour decay factor and I have 500 milligrams, how many milligrams will I have 1 hour later? Okay, what does B mean? If it's the 1-hour decay factor, what does it mean? It's the so at some point, if you're going to understand exponential functions, you got to know how to describe a decay factor. It's a multiplier on output to get the next output. It's a multiplier on output to get the next output. Therefore, after 1 hour, how much do we have remaining in the system? This is the multiplier on output to get the next output. Therefore, the next output is 500B. 500B. How much do we have after 2 hours? You're going to multiply by b again. So therefore, how much would you have after 5 hours? In this 500 times b to the 5th. So, but we know that that's 75. We already know that that's 75. But if b is our 1 hour decay factor, then it's 500 b to the 5th. And now we can solve for b. Now we can figure out what that 1 hour growth factor is. Okay, so it turns out to be what? If you solve this for b, you get 75 over 500 is b to the 5th. So b is
0.15 power of 1 over 5.
yeah, so 75 over 500 to the
Power of
1/5 power, or 0.15 to the 1/5. And what is that value? So we just get a value for that. I heard two very different things. 0.684 is what I'm hearing. 0.684. All right, what's the 1 hour percent change? What's the 1 hour percent change? Negative 31.6 or something?
Yeah.
Okay, so write the function g of t. Who's got the function g of t?
500 times 0.15 to the 1/5 and all that to the power of t.
Nice. So the 1 hour growth factor is the 0.15 to the 1/5, and then after t hours, it'll be to the t power. You'll multiply by that t times. Okay, so we need to understand the derivation, but then we can also look and see what's happening. If the 1 hour decay factor is to the 1/5 of the 5 hour decay factor, so then what would the 1 minute decay factor be? So if we've got the 1 hour decay factor here, 0.15 to the 1/5, what would the 1 minute decay factor be?
All that to the power of t divided by 60.
Times 60. So this is the 1 hour decay factor. We want the 1 minute decay factor. Jacob, what do you think?
I still haven't figured it out yet, sir.
You were thinking about it, though. Okay, but how did you get that? How did you get that?
I did that by making it the 1/60th. Making what? The minute. I took 0.684 and took it to the power of 1/60.
Right. So if we knew what before, we knew the 5 hour, and to get the 1 hour, we took the 5 hour decay factor to the 1/5. So now we know the 1 hour, and we want the 1 minute. We're going to take that 1 hour decay factor to the 1/60th. 1/60th. Okay, so look at what's going on here. Here's the 0.15 was our 5 hour decay factor. Took it to the 1/5. We got the 1 hour decay factor. Take that to the 1/60th, and that whole thing in the square brackets then is the 1 minute decay factor. And remember, whatever you're, so if this is a unit of minutes, then everything in that parentheses has to be a decay factor for minutes, and that's what that is, right? Those have to match. The unit on your exponent has to match the base unit, the factor that it is for the base. Okay, see if you can finish this off here. So I want you to find the 1 minute percent change, and then let D be the number of half days since taking the medicine, and you're going to find the half day percent change. So find the half day formula, if D is the number of half days, and the half day percentage. So you got 3 more things to do. Anyone got the 1 minute percent change? I'm hearing negative 0.63%. Yep. Now that's percent. Why? Because the 1 minute decay factor is 0.9937. And so this is truly percent. It's less than 1%. Okay, so now if we want to come up with a formula for half days, we need the half day growth decay factor. How am I going to get the half day decay factor? How about back there in the free shirt with the headphones on? Yeah. How am I going to get the half day decay factor?
You take 5 hours and you
Use the 1 hour. How about the 1 hour? Use the 1 hour.
1 hour. So you just set the 0.5.
What's that?
You set the 1 hour to 0.5. Oh, half day. Sorry. 12.5. Not 12.
Okay, so we'll take the 1 hour decay factor and do what to it to get the half day decay factor? To the power of 12. Now this is a multi-unit, right? This isn't partial unit. So we're going to take the 1 day and take it to the 12th. So what will that look like? It'll look like this. That'll be that 0.15 to the 1/5. That's our 1 day, or sorry, 1 hour. Take that to the 12th. And that'll be that number, that'll be the half day multiplier. And so then the percent change, did you get it? So there's our half day decay factor. Percent change is? Does that feel right? So you take ibuprofen, 12 hours later, it's saying that almost about 99% of it will be gone out of your body half day later. Makes sense, right? Okay, so quiz.